So hopefully when you're drawing these out, you start to get a better feeling for what I'm talking about by, yes, they're called quantum numbers, but really they're just addresses for where electrons live. Okay. So when we are, if you get that idea that it's a description of where electrons are going to be, I'm going to then take and describe how they fill up, how the electrons fill up around an atom. Because an atom like sodium, which has 11 electrons, has to put its electrons somewhere, and it's going to be in these running paths, okay? So let's look down here as a quick description, a summary of what kinds of running paths or homes for electrons they have. One, it's going to be different distances to the nucleus. They're going to have a 1 distance, 2 distance, 3 distance, 4 distance. Okay, how far you are from the nucleus. That's going to be part of the description. 2, it's going to tell you the shape of the running path. Is it a sphere? Is it a figure 8 because it's got 2 lobes, just like a vibrating string can have 2 lobes, or is it going to have 4 lobes? The third thing is going to be, are those lobes directed along some axis? A sphere can only be pointed in one, so there's only one kind of sphere. That's where you start getting, say, that 1 distance to the nucleus has a sphere. It's only one direction. You can't rotate it and look any different than any other orientation of that sphere. But if you look at the p orbitals, which are, vibrating back and forth like this on the x-axis or on the y-axis or the z-axis, you can point them in 3 different directions to avoid the other 2. So there are 3 individual paths that are best at avoiding the others in there. So there's 3 individual paths for p's, giving a total of 1 s and 3 p's, or 4 orbitals that can be run at 2 distances to the nucleus. 3 distances to the nucleus, you have 3 shapes. You still have the s, you still have the p. The sphere that's 3 is, is now bigger than the others. It's 3 sphere, 3 distance long sphere, 3 distance long figure 8, up, down, in and out of the page. And then there's these figure 8s, the clover leaves that look here as well, d orbitals. So if you add those up, 1 sphere, 3 figure 8s, plus 5 total d orbitals, that's going to be 9. 1 distance has 1, 2 distance has 4, 3 distances has 9, 4 distances has 16. Do you see the pattern? What would 5 distances have? Square that, 25 different paths. 6 distances would have 36 different paths. So as you get the distance to the nucleus further, you add one more shape, which has a lot more capabilities, but to figure out how many different running paths or the homes for electrons there are, you square the distance from the nucleus, and that's how many running paths there are. Now, it also tells you how many electrons can be there, because 1 electron spinning in a clockwise rotation and a counterclockwise rotation can sit in every path. So for 1 orbital, you can have 2 electrons. 4 orbitals, you can have 8 electrons. 9 orbitals has 18 electrons. 16 has 32 electrons, right? Every running path has room for 2 electrons. So let's say if I'm going to throw a bunch of electrons onto an atom, where are they first going to go? Atom is positive, electrons are negative. They're going to try to get as close to possible as they can. So let's take a look at what that means. Take these off there. Oh, come on. The first electrons are going to get to the 1s, the closest sphere they can. So when you get 2 electrons in there, you'll notice that you've filled them all up. Here's the total number possible to fit in an s. So once 2 electrons go in there, you'll be full. Let's say I'm trying to get to sodium, which sodium has 11 electrons. So the first 2 go to 1s, and they fill up that 1s. That's now got 2 electrons in, spinning positive and negative. I got to go to the 2 distances to the nucleus. Got to move out to the next sized sphere, and I'm going to fit 2 in there. So I got 2 electrons here, 2 electrons there. I still have 6 more electrons to go. So I got to start putting them in this pathway, and this pathway. So I can put up to 6 more electrons in there. Yeah, that's great, because now I've got 10. Sodium has 11 electrons it wants to put someplace. So I've got 1 more. Where I'm going to go is follow these arrows in this system, and I'm going to put 1 more here at an S. That means the 11 electrons for sodium, which has 11 electrons, okay, that's where the atomic number goes down here, right? That's the number of electrons. And they're going to be in a 1s. There's 2 of those. They're going to be in the 2s. There's 2 electrons there. And the 2 p's are going to be filled. There's 6 there. And then there's 1 in the 3s. So each of these numbers are quantum numbers. 1 distance to the nucleus sphere, there are 2 electrons. Okay? So there should be actually 2 quantum numbers for that, but that's telling you how many electrons are in each of those paths. 2 distance from the nucleus. In the sphere, there is 2 electrons. Stop. There we go. Anyway, you get the picture. Now, if I want to go to scandium, let's go to scandium because that's a big element, scandium. And if I look in the periodic table for scandium, it is element 21. So let's try that guy next, scandium. Okay. Again, he's got 21 electrons. That's where the number for electrons goes, or protons. That's the atomic number, as a reminder. 21. Okay, this is 11. Here's 21. So I'm going to start putting in electrons, just like I did here. 2 electrons go here. 2 electrons go there, 6 electrons go there. That's 10 electrons. Okay, so I'm going to just start writing them in. In the 1s, I have 2 electrons. That gets filled. 2s, I've got 2 electrons. That gets filled. I'm going to go next to here, to the 2p. That can take 6 electrons. Right? That fills at 6, or the left, right, up and down, in and out of the page fills at 6. When 2p is done, I'm going to go down here and follow the next one, which is 3s. Okay, and I can fit 2 more there. I'm still trying to get to 21. Right now, I only have 12. So I got to still find some more homes. Once 3s is filled, I'm going to go to the 3p. That can take 6, right? 3p can take 6. That's the max right here. Then what's next? Do I go to 3d? Well, the D shape takes a little bit more energy to get it to vibrate in that pattern, and it's easier to fill up a sphere, even though it's one distance further from the nucleus. So the 4s goes next. So I go from 3p to 4s. That's where this changes a little bit. And then that's what these lines are called the Aufbau process. Then once I fill here, I can go back to the other end and start going back to the 3D. Right now, I have 20 electrons, and I need 21 homes. So I'm going to go after the 3D. And there's where my last electron is. So that's how I would fill that. Okay? All those electrons are in those shaped orbitals. Now the last thing I want to mention is, what would happen if I was a scandium but I lost 1 electron? I was an ion and I charged 1. And then the answer to that is that the electrons don't come out in the same order they went in. They come out. They go in according to Aufbau, this pathway up here. But they come out based on where they're farthest from the nucleus. So when you look across here, which one's the farthest from the nucleus? The 1s, the 2s, 2p, 3s, 3p, 4s, or 3d. The 4s is farthest, and you have to take it from the largest principal quantum number. The largest 4 is where the first electron comes out. So it's going to look very much like this, except that this is the electrons that come out when it's a scandium plus 1. One of the electrons is going to come out of there. Oops, this should be a 1, not a 0. Okay? Because you're going to take 1. If you had plus 2, it would become a 0. I would agree. But this is scandium plus 1. All right. Let's work on writing out the electron configurations for these atoms that are on your worksheet.